Hello gentlemen, welcome to your video on section 2.3 called Atomic Theory and Atomic Mass. Now the first thing we want to do is talk about what an atom is. An atom is the smallest representative part of an element, the smallest component of that element. Now we know that atoms can come together to form compounds. And to talk about what a compound is again, compounds are materials that can be broken down chemically into two or more kinds of atoms. Or you think of it the opposite way, is that two or more kinds of atoms can come together chemically to form a compound. Now in our investigation for this section, we talked about and looked at atoms and compounds. A new type of reaction was introduced in this section. It's called a single replacement reaction. This is where we have one singular thing, our atom, reacting with a compound. In this case, we had solid magnesium strip reacting with your blue solution, which is copper sulfate. It's aqueous solution. We know that that is a homogeneous mixture. When these two reacted together, we saw bubbles, we saw different things forming in our beaker. What was happening was this. It was a replacement. This magnesium was replacing the copper. And the copper came out, magnesium went in. When that happened, we get this on the other side. The darker blue solution was magnesium sulfate, which is a compound, and which was liberated was the copper. So those little black or brown pieces of what appeared to be dirt was actually pure copper metal being liberated from the copper sulfate. So this happened in your chemical reaction. We're studying this to talk about the general concept of atoms combine to form compounds. This is a well-known topic now, a well-known statement, but back in the late 1700s, early 1800s, people were just starting to figure that out. Especially this one guy here. This one guy, Joseph Proust, who was a French chemist, he knew this. They were just discovering this, and he proposed a law based on the fact that atoms combine to form compounds and or molecules. He called this law the law of definite proportions. It stated that a given compound always contains atoms in a certain or specific proportion by mass. He said that atoms combine in whole number ratios so that their proportion by mass will always be the same. Let's talk about what I mean by proportion by mass. Let's use water as an example. Now water will always be made up of 2 atoms of hydrogen and 1 atom of oxygen. Whether you're here in America or China or Alaska or Africa, wherever you are, pure water will have this chemical formula. It sounds obvious to us now, but back in the early 1800s, they didn't know that. So always made up of 2 atoms of hydrogen, 1 atom of oxygen, we have H2O. So we have hydrogen. Hydrogen has a mass of 1. We'll talk about the units of this 1 later on, but it's a mass of 1. Oxygen has a mass of 16. If we compare these two masses, then we'll see that if we go oxygen to hydrogen, we have 16 to 2. If we're talking about the compound water. That's a 2 here because I have 2 hydrogen atoms. They both have a mass of 1 apiece. So I'm talking about the mass of my water. Oxygen accounts for 16 of that mass. Hydrogen accounts for the other 2 of that mass. If I compare this in form of a ratio, I get 16 to 2, which reduces to 8 to 1. This is the ratio of oxygen to hydrogen atoms in water. Meaning, in every single water molecule, water compound, H2O, in the world, the masses of oxygen to hydrogen will always be 8 to 1. I'll have oxygen is 8 times more massive than hydrogen when it comes to water. That relationship will always be the case anywhere you go in the world for pure water. And the same is true for other compounds. They'll have their own distinct ratio of masses. That is proportion by mass. Now this law opened the doors to a lot of other chemistry. A gentleman, an English chemist by the name of John Dalton, was able to form some pretty serious postulates, which means hypotheses, some hypotheses based on this law from Proust. Also, he's doing some of his own work where he would do work with the atomic theory. So he formed 4 hypotheses or postulates on atomic theory. His first one was this: matter consists of small particles called atoms. Seems simple to us, but back then it wasn't such a given. Also, he said that all atoms of a given element are identical, but atoms of one element are different from the atoms of all other elements. So atoms of the same element are the same, but atoms of different elements are different. So copper versus magnesium, those types of atoms are different, but a magnesium atom in Africa is the same as a magnesium atom in France. Third postulate. Atoms of one element cannot be changed into atoms of a different element by chemical reaction. Atoms are neither created or destroyed in chemical reactions. We know that. And this is just a restatement of the law of the conservation of matter, which you studied in chapter 1. His fourth postulate was that compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kinds of atoms, which are expressed in small whole number ratios. This is kind of just a restatement of the law by Joseph Proust, the law of definite proportions. He just kind of put it as one of his hypotheses as well, added a little bit more on it, talking about the whole number ratios portion. What that essentially is referring to is, our example, water again. That water is H2O. These are whole numbers here, 2 to 1. I'm not saying, 2.5 hydrogens to 1.2 oxygens. No, these are always going to be whole number ratios in your chemical formula. And he's saying that water will always be 2 hydrogens to 1 oxygen. It will never be H3O, H2O2, or HO. These will never be water. Water is always H2O and only H2O. These will be other things. That's hydronium, that's hydrogen peroxide, that's hydroxide. Different things, not water. Now I have a question for you. We're talking about mass a lot. Well, how much does an atom actually weigh? Well, we have that answer now, but early scientists had to figure this out in a different way. Atoms are so small that early scientists could not get an accurate measure of their true mass. Thus, they had to create their own system. They created a system based on comparing the masses of atoms to obtain their masses relative to other atoms. So they compared the masses of different atoms. They didn't know their actual mass, but they could compare. This one's really big. This one is not so big. But this one's actually 4 times larger than this one. So they can compare their masses in that way to kind of figure out how their masses related to one another. This is what we're doing in our investigate for this particular section. So we have magnesium, solid magnesium, reacting in copper sulfate. We're producing magnesium sulfate and solid copper. Now we're going to be comparing the masses of the magnesium that we started with in grams and the copper that we finished with, that those brown specks, in grams. We're going to compare them just as scientists did back in the early 1800s. We'll take the mass of magnesium, compare it to the mass of copper. What we'll figure out is how the masses are relative to each other as far as their sizes are concerned. We'll figure out the relative size to one another. How much bigger is copper than magnesium? Or how much bigger is magnesium than copper? We can figure that out through this chemical relationship here. So gentlemen, please take notes and be ready to discuss this last concept in class tomorrow. Adios.